This is the second video in my introductory tour through webgl. In the previous video, we talked about how to get started, and really it was a lot of background information on webgl and OpenGL and the way it works. We didn't get into any of the GL code really, just a little itty bit, and so today we'll look at that, and we'll talk about the shaders, right? So in the previous video I described the way that the drawing pipeline works in OpenGL, and there are these two main components that we call shaders that we use to generate images: the vertex shader and the fragment shader. And the vertex shader, which we'll look at first, its job is to basically go from the various objects in the scene and do all the transformations to place them in the world, and rotate and scale them or what have you, but also take into account the camera, take into account any perspective and the screen, the geometry of the screen. And once the vertex shader is done, you have a list of vertices, or a list of triangles, if that's what you're rendering as, that you will then pass through into the fragment shader. And I made some analogies yesterday in terms of, or comparisons rather, to what we currently are graphics engine, and I think actually it could be a little bit more targeted in terms of what's what. So the I said that like the scanline conversion function is sort of like your what we would think of as the fragment shader, but really it's the draw polygons function, right? That goes through the list of vertices and then renders them, calling scanline convert and doing some other stuff. So that's really right. So the vertex shader, you can think of the vertex shader as everything that our graphics engine does up until you say draw the polygons, right? And the order is different because we're kind of drawing things on a shape by shape basis, which is a little bit different. But anyway, so what we want to look at is, okay, how do I define a vertex shader? What goes on in there? Remember, the goal of the vertex shader is to handle, and actually it's over here, I have it on this page open, right? We've got whatever the object was, but then there's a model matrix which places it in the world. Then we take care of the camera and do a view matrix. Then we do projection and clipping, and lastly output some screen coordinates, right? So all this has to be programmed into the vertex shader. Right? And the vertex shader you can think of as like a whole program in and of itself, rather. So right here's once again the demo code that I have right now. It renders an amazing white square, right? That's it. And the HTML, which we're probably never going to look at again because nothing needs to change about this, right? That's all we've got going on here. And the key is, well, actually, I will make note of the two script tags, right? So the first script tag is grabbing source for this GL matrix JavaScript library. And it's interesting, I'll point it out later at some point in the documentation here. It says, oh, you might see an error because this particular type is not defined, in which case just grab this source code. So that's what I've done, because I got that error. But the code that I have written is this WebGL demo simple. Cool. So let's find it. WebGL demo simple. Cool. So this chunk here, actually, before we go there, this chunk defines the vertex shader, okay? And in fact, this code is exactly the same as the code you see here. But there's perhaps a little bit of JavaScript oddness here, but also some things that maybe you'll find familiar. So the entire vertex shader is defined. It's a variable, right? It's this VS source, and it's a string. So first off, just a little JavaScriptiness. Um, Notice that there are backticks used here, but Emacs seems to think that this thing is a string, and it is. I was actually not aware of backticked strings in JavaScript, and so I thought that something super fancy was being done here. Turns out you can actually do some really cool stuff with backtick strings in JavaScript, but the one of the key features is that it's similar to using triple double quotes in Python. So you can define a string where the new lines and tabs and all that are retained, but also you don't have to enter new lines by doing \n. You can just make a multi-line string, and all the white space and all that stuff is retained. And I have a link here. Once again, source code's not up right now, but I will be doing that later once I get the video done. And I have this link here, which I thought was a nice overview of how backticks work. So, right, like it could be just like a regular thing. This is a neat thing here. You can actually look how you build up this string with the sort of, it kind of looks like shell scripting, right? The $ and name, and it's going to use the name variable and pull it in, which is pretty cool. You can even call functions. There's some neat stuff. And you can do multi-line strings, and then there's tag templates, which started to go off into, all right, I don't have time to figure it out. So they're strings, and the reason I'm fairly certain that the reason why they're being used here is just it's easy to make something that looks like code with new lines and indents and stuff as a single string. Because what we're actually doing here, remember that the fragment shader, sorry, the vertex shader is like a program, right? We need to know the matrix. We need to know the model matrix, the projection matrix, the vertex list, and we need to know like what to do with all those. And so what we have here, what you see here is actually, this is JavaScript code in a string. And the reason why, and we'll see this later, is that the way that webgl works is it's going to use this source, this string, essentially as source code, and it's going to build the shader program and attach the various internal GL stuff using this as the source code. Okay? So if we look at this, we'll see this is a very simple version, but we have 3 variables. So this attribute and uniform, right? Those are not normal JavaScript-y things like where's var, where's const. So these come from, and in fact, I should go back up. So if we're looking at the web page here, the OpenGL-ES shading language, which actually well, this is actually really useful stuff. That was not the website I thought it was. Hold on. Yes. Here, so this is a data in WebGL, so this is still under the WebGL API. These are GLSL, so it's the GL shading language data types. And you can actually get much more detail on it on that page that I was scrolling through a moment ago. But they're just different variable types: attributes, varyings, and uniforms. And I got some information here. Like attributes are only available to the vertex shader, and uniforms are available to the vertex and the fragment shader and things like that. And we'll go through more later. But that's what's going on there. So those are not like brand new JavaScript-y things. They're part of the GLSL framework, and that's a piece of why this is a string. Is right. It's not a JavaScript thing, but it is basically WebGL is going to compile this string into a graphics engine, all right, your shader, as it were. So what do we have here? We have attribute vec4. So also note that this is not quite JavaScripty. It's giving a, this is the, variable kind of, something that describes the variable, but vec4 here, that's like the type. It's kind of like int or, double. And it's a vec4. It's a vector with four pieces. I don't want to use the word attribute. And where each entry rather is 4. Now, once again, this is not vector in the sense that we think of in graphics, right? Like a surface normals type of thing. This is like, oh, computer scientists refer to vectors or refer to arrays sometimes as vectors, right? So, so we've got vec4 and then vertex position, and this is going to actually be all of the vertices. Okay, this variable is going to represent all the vertices. Okay, and then we have the model view matrix and the projection matrix, and notice mat4 and mat4. And the mat4 type, this is what I needed, that extra library that I included in my HTML source. Okay, so, and we look back at the, not data in here, but this, right? We know, well, what do? We take our model matrix, our projection matrix. Notice we're not actually looking at the view matrix right now, which is fine, but we could add. And actually, if we scroll all the way down, there was that matrix multiplication projection type view times model. And notice the main here. It says, hey, GL position equals projection matrix times the model matrix times the vertex position, right? And that's it. So this vertex shader just says, okay, when we want to make positions, when we want to get out of this the actual vertices, we're going to multiply the projection matrix by the model view matrix by the vertex position. And notice using the regular old, sort of vanilla, as it were, multiplication operator, the asterisk here. Once again, this is a string where we've kind of made up some code. Great. So that's the vertex shader source. Now you're probably wondering, because I certainly was, okay, but how do I get data into these things, right? I've just defined, this is a fairly abstract vertex shader, right? I'm saying, okay, I have vertices, I have a, say I have a model matrix, let's say I have a projection matrix, then to get the actual vertices, I multiply them. Seems like a fairly abstract thing. And the key is that we attach meanings to these things later. Like, this is the source code for the shader, and then we're going to be able to actually interact with these variables through other GL functions. Okay? So that's the vertex shader. And if we run main of the vertex shader, we'll get a list of vertices that we want to actually render. The fragment shader, so once again, it's another one of these backticked strings. And if we look, right, the fragment shader is about taking the vertices and, excuse me, rendering them, right? Putting them in the screen, rendering all the pixels and all of that good stuff. And so if I'm just, right, this program is just rendering a white rectangle. And so you'll see that the fragment shader that I have just says set the fragment color to a standard vec4, and it's 1111, and that will be red, green, blue, and the alpha, the transparency channel. So it's all red, all green, all blue. So this is not a 0 to 255, it's actually a 0 to 1 scale. And so it's all for red, green, blue, and then 1 for transparency, or really 1 for opaqueness, right? It is not transparent. Cool. So that's the source for the fragment shader. Okay. And now comes a whole lot of GL stuff to basically take this source code we've written and give it meaning in the GL framework. And actually, the order that I've written the code here is slightly different from the order here on the web page. And it's, I think it's just because they do a big chunk at once. But the way that I've written these functions, of course, this is just a function, so I could write it whichever way I want. But I wanted to think about, okay, what's the first thing that we do to these strings when we want to actually create a program? And so what happens if we go all the way down, and we'll get through this. Notice all the things happening here. Right, we grab the canvas, we init shader program. That's the first thing we do, right? So it's this line here that calls init shader program. That's the first thing that actually does stuff with our shader code. Init shader program, and if we look at that, it calls, and that's here, first thing it does is called load shader, and that's where we are, right? So the first actual function, so kind of doing the stack trace as it were, the first function we hit is load shader, and it's going to take, essentially it's going to turn the source code into a shader program in WebGL. It takes 3 arguments, and GL is the WebGL context. So that's that's what you get when you grab the canvas element in your JavaScript and then you initialize the context as WebGL as opposed to another graphics context. So this is GL is a sort of instance of WebGL. Great. So it's got all the WebGL goodness inside. Type. We're looking at just 2 types of shaders, vertex and fragment, but they do different things. So we need to pass what the correct type is. And lastly, source. And the source is going to be one of these 2 strings, right? So it's a string that represents the source code for the shader. Cool. So this function, first thing we're going to do is create a generic shader, right? I'm not giving any of the source. I'm just saying, hey, I've got a type. I know what type it is, so GL create a shader. And so that's what I've got. And it'll make a vertex or fragment shader. Then, and whatever sort of the underpinnings of that are, which I don't know, and don't think we would have time to get through all of that stuff anyway. So it makes a shader, sort of generic shader. Then we set the source. So we say, all right, we've got this shader object. Now let's basically set the source to the shader, to the source we've defined. Right? So I've defined this source as VS source or FS source. And then you compile. So notice the language being used here is it's very much like, oh, we're writing a program within our JavaScript program. And so we set the source code, and that's why it looks like source code, because it is. And then we compile it. So we compile the shader program, and at the end, it will be a WebGL shader kind of object that is attached to the code that we've written. Now, one quick thing that we could potentially do to see a difference is we could, for example, get rid of the model matrix, and that would be dumb, but that would result in a different kind of shader than if we included it, right? So that could change the main here, and that would be a different kind of source there. Error checking is always good. You want to know, right? We don't know a lot about what's going on in that compile or any of these, right? Create, set the shader source, or compile. So let's make sure that worked. If it didn't, then we'll print out some information about it and then move on. Cool. So this function is all about taking that source code and turning it into a GL shader that's specific to the code that we've written. Great. So now let's look at the init shader program. So here, once again, we are taking an instance of GL. We're taking the vertex shader source and the fragment shader source. And the first thing we do is we generate the shader from load shader. So notice it's very much the same call. The only difference is we change the source, and we've got a vertex shader or a fragment shader as the type. So first thing this function does is give us a compiled shader with our source code. Now, oops, nope. We actually, so like the word shader in program is sort of been using fast and loose because in here in the the design here it says, okay, basically let's create the shader program, and the idea is really we have a GL program which is the combination of the shaders, right? So in order to do a full graphics engine in GL, we have a vertex shader, we have a fragment shader. So let's create, and this is kind of similar to what we did in the load shader function, right? We create this kind of generic GL program, and once we've done that, then we say, well, actually, this generic program is going to have the vertex shader that we've created and the fragment shader that we created, right? So we're attaching those, and then we're linking it. And it's sort of a kind of loose comparison, and I say loose, it might be stronger or weaker. Just I haven't gotten into the details of what's going on under the hood. But this is kind of like the linking step in, say, GCC, is what it looks to me, right? We compile, imagine the shaders that we get here after load shader is kind of like the .o files. We've compiled each of those separately, and now we're linking them together, and we attach them, and then we link them to the shader program. So now the shader program has hooks into the different shaders. Okay, so that's what this does, is when this function is finished running, then we have ourselves a webgl program that will contain, that has both the vertex and fragment shader information. Okay, so once we get through this, basically what we've done is we've defined this shader program, but we have not done, what we haven't done is provided any actual objects to be drawn. We talked a little bit about color because it's just drawing a white rectangle. We'll see other options later. We haven't talked about the projection matrix or the model view, the model matrix, or how to set those, right? That comes later because those are represented by these variables here, but we haven't set them. So it's sort of interesting in that the program we end up with over here is really just a sort of framework of a program, and we're going to set the variables elsewhere. So render a square. So this function here called init buffers is going to be where we deal with the buffers for, that's what we're going to refer to these things in our source as, is we're going to talk about these as buffers, right? So your vec position and so on. And I'm actually going to skip ahead a little bit because one thing you'll notice is that init buffers just takes a GL object, right? It's that webgl context, and it doesn't really refer to any of the shader program stuff. So how does it get linked in? But we'll see that in a moment. Basically, we once again create like a generic buffer, we bind it as a position buffer, right? So this is going to be a list of vertices, okay? That's all. That's what this is going to be, a list of vertices. So it's a position buffer as opposed to another type. Now we create an array of positions. So this is actually defining our shape, okay? And that's an important thing. You're like, well, how do I draw the square? I'm drawing a square by defining the 4 vertices of that square. Right, so it's a little more generic than having to make it out of triangles, for example. You're saying these are the vertices of what I want to draw, and there we go. Okay, so this is a square. It's bounded. It's -1 to 1 in all all your directions. So that's it. That's the only object I'm drawing. So that's what I get there. Now we pass this list to webgl, and we're like, hey, attach the buffer, and notice we return a single. We're returning a single element, like associative array, or what you might call an object in Java, where position matches this position buffer that we've created. I'm actually going to modify this in a moment, but let's just do that. We'll do this one for now. So here, we've just defined 4 points, and we've made ourselves a rectangle, or square, really. Well, I guess a square is a rectangle. Great. So that's what's going on there. So now we want to draw the thing. So this is a draw scene, and this is where we deal with some of the other matrices we want to interact with, the projection matrix, the view matrix. So draw scene, we set a clear color, and basically this is just some initializing. Okay, let's clear out whatever's in the buffer right here, right? All of that says, great, we are ready to start with a blank slate, and it's going to be black because that's the clear color we set. Cool. There's a depth. You can actually set how much to clear based on your Z values, which is pretty cool. You could like leave stuff in the background that you wanted while just modifying things in the foreground, which is a cool thing. Anyway, here is where we start to build up our matrices for the vertex shader. So this is actually going to build up based on a projection. So there's this field of view, which is 45 degrees. And once again, just so we're clear, this code does come from, so here's the buffer stuff. This code comes from here, right? So you can go through this in more detail. Here's that warning about the matrix class. And so we're defining our view plane. Remember that the projection matrix also clips, and so we're defining not just our X and Y clipping plane, but also our Z, which is perfectly fine. And notice the projection matrix. We create a generic mat4, and here webgl has a built-in WebGL always has a built-in make a perspective matrix, right? Mat4, well, it's the GL matrix class actually, but mat4.perspective. So give it basically just a projection matrix that's got nothing in it. Define the field of view. Define the aspect ratio. Notice the aspect ratio here, by the way. This is the screen, the client width, client height. Those are the actual dimensions of the canvas. And so that actually kind of builds into the viewport transform. So it's kind of put the projection matrix and the viewport transform all together. Cool. And then Z near, Z far, right? So we do the Z clipping if we need to. So that generates our perspective matrix, our projection matrix. Notice this just makes it, we haven't actually attached it to the shader program. Cool. Then we do the same thing with the model view matrix. Now this one's going to look a little bit familiar, I would say, right? Because all we're doing here is translating, right? Model view matrix, and so the destination matrix is where we want to put the solution. The matrix we're translating, we could have other temporary or intermediary matrices along the way. And we're translating, so the amount to translate is 0, 0, and -6. So we're actually going to move the square back by 6 units. And something to think about, remember that I said, when we define in the previous video, the clipping plane is defined as in the bounds of 1 to -1 in all, in x and y. And my square, go back up. Whoop, sorry, I went too far. And went too far again. The square is -1, right? It's the full area. And so what we're doing is we're moving it back by -6 so that it's actually, we can see the projection because it's going to scale it down a little bit. And so now we've got our transformation, or rather our model view matrix. And we could add transformations to this if we wanted to. But right now, let's just leave it as such. Cool. So we've defined the projection matrix. We've defined the model matrix. Now, how do we deal with those matrices and our buffer of positions? And that's what this is. So couple things going on here. Number components. So we're just doing a square. We're not doing XYZ components, just XY. So each entry in my list of vertices is just 2 components, XY. Great. Normalize, so type of data. Normalize, right? This is the sort of thing you might want to do more if you're into 3-dimensional stuff and you need to normalize each of your values, but we don't need to do that here. They've already been normalized also. Like you could also do it for things in 2D if you've defined the vertices in like, if instead of bounding them in 1 and -1, you've bound them, you've made them much bigger, and you're like, no, let's normalize them so we work within the 1 to -1 plane for everything. So you could do that. So stride, I actually found that name interesting. That's like how big you step through your list of vertices. And if you set it to 0, it just bases it on num components, which makes sense, right? So if I have my list of vertices, I'm going to go through 2 at a time, and that's kind of what the stride is. Cool. And offset if there was other stuff. Like I actually not certain how you would use that yet, but it's there. So we define those things, and really, the things that I think you might change at some point if you want to. Well, if you're going to do 3-dimensional, this would end up being 3. And normalize, you might want to change that to true if your vertices are not normalized already, or within a reasonable within reasonable boundaries. So now what do? We do some more GL stuff. And once again, I'm like speaking through this. Maybe you just read through the documentation and you get it all, and that's fine. But were we in school, I would spend some time pointing all this stuff out. You'd probably ask questions. I'd attempt to answer them. I might also just say, I have no idea. Let's look it up. But that's what I'm trying to do here. Trying to provide some resources for you. So we take vertex attribute pointer, we put all these things together. Sorry about the baby noise in the background. We believe that he is currently teething. He seems to be ornery the last couple days. Anyway, we set up attribute location. So notice this program info. And you're like, where did that come from? Program info is a function here, and buffers. So program info is going to be related to the GL program that we've created. Buffers is going to be related to the buffers that we've created. Okay, the buffer with the vertices, right? So, and notice here, to be clear, buffers.position. And just to remind us, actually, I can bring up the code because it's the same code. Return, right? We init buffers and we return this JavaScript, associative array, and position is the position buffer right here, right? The list of vertices. So vertex attribute pointer or attribute pointer, right? So we bind the position buffer to gl.array buffer, and then we say vertex position from within program info, which is going to be related to the program we've compiled. Then we deal with non-component types, normalize stride, so we initialize, right? We set all these variables and then we initialize a vertex attribute pointer. And then we grab the vertex position piece from the program info. Now notice program info.attribute locations, vertex position. That's inside the webgl program. Here we have program info.program, and that's going to be the actual program that we've created. Then we set our matrices, and here the uniform matrix. So program info.uniform locations.projection matrix, we set it equal to the projection matrix that we just defined, and the model view matrix that we just defined. And then we draw the array. So we go through the array triangle strips, so it's going to be making them based on triangles. So it's going to turn it into triangles and do all that stuff and generate it for the GL program that we have here. That was a lot. There's a lot going on here. It took me a few times of reading through this code and really trying to map it to what is going on. I hope I helped. So that finally gets us to main. All of this to make a square. Obviously, you'd probably want to use WebGL for not making just regular old squares. You probably want to use it to make really cool 3D stuff, but let's do something simple because then we have to add a bunch of other things. So, in main, which, by the way, right, that's what loads when we load the window here. In main, we are starting by pulling the canvas, right? This is the same as before. Now we're going to initialize the shader program, right? So here, that does all that shader program stuff. So shader program is now the shader program, right? It's got the compiled and linked vertex and fragment shader pieces. Great. So what we need to do is package this all together in program info. And that is that is what the WebGL instance turns into. So the program info is the combination of the shader program and the data that we have been putting together in the buffer section, right? So program info, program is the shader program. Great. Locations. So the locations, and notice this is where we finally get to tie our shader program in with the vertex position piece. So program, attribute locations, vertex position is going to going to refer to the a vertex position in our source, right? So on this side, let's like go all the way back up to the top. A vertex position is what we're saying attribute locations refers to, and that's how it ties back to this string source code that we started talking about at the beginning of the video. Now, what does this actually mean? Well, let's actually go to the draw, because this is where, right, program info is this argument to draw scene, and vertex position, attribute locations, like where did that come from? That is here. So we're saying, oh, we're actually binding this vertex attribute pointer to the vertex position, which is going to then, we will then get a hook into our source code as the a vertex position. And then similarly, uniform locations, projection matrix is going to attach to U projection matrix. Model view matrix is going to attach to U model view matrix. And notice those actually happen here, right? We say uniform, we're going to say uniform matrix is going to be for the projection matrix that we get from program info. That's going to refer to the projection matrix that we've built here. Well, here. And similarly, the model view matrix is going to be referring, so it's going to say, oh, hey, it's this thing from program info, but really we're talking about the thing in our source code. So we create our program info. And then we have, we say, oh, the buffers, we're going to init. And remember, that's this init buffers. It really, and I'll go up here, this is just our buffer of positions. We'll see other buffer examples later. And then we call draw scene. And that is where this amazing square comes from. All right. But just a few things like, okay, how does this actually, can I modify this? Is there anything I can do? Well, one thing we could do is let's get rid of one of those positions. Oh no. Yeah, that was dumb for a number of reasons. But instead, let's make this negative 0.5 and 0.5, right? So I like modified it just a little bit. And now it's not a square anymore, right? I changed what this looks like. So there we go. So there is something happening. These are the points. Similarly, my translate, I could also decide that I want to move it over, -6, to make it really small, -20. It got smaller because it's further away. Or I could make it, -1, which would be not very far. And now, right, it's the entire, it's most of the screen, except that little slice because I made it no longer. And there we go. And if you wanted to add other transformations, you could do that. There's a mat4.translate, there's a rotate, there's a scale, and we can do all of those things. So that's how this all comes together. It's really a lot if you wanted to just draw a square. But in the next video, I'll talk about doing some more transformations, doing some color stuff, and then we can get to some 3D things. So there you go. Hopefully this helped make sense of some of these things if you are interested in it. All right.